So we finally come to talk about dark matter at the colliders. Okay, so just first some general remark. Okay, so the motivation for thinking about dark matter is very different from thinking about anything else, any other new physics in the standard model or beyond standard model. Okay, it's not from any requirement that we have to have dark matter. Okay, a theory without dark matter is there's no problem with that theory whatsoever. Okay, so the motivation to think about dark matter is just it's there. Okay, so we wanted to understand what dark matter is. Okay? We have already discovered the dark matter. We wanted to understand what dark matter is. Well, just at some very leading level, there's a huge range of possibility of dark matters. Okay, so just the mass, for example, the mass of dark matter can span a huge range. Okay, anybody knows the upper limit of the mass of dark matter? So the best thing I know is to look for this huge object in the universe. What you do is let's say you focus on a star. Okay, you look at the star, and if a dark matter comes through it, and well, you won't see the eclipse. So I think if a dark matter particle goes through it, but the gravitational field around the dark matter particle will focus the starlight briefly, and go away. This is called the microlensing. So you'll see it. You see those blips, and the starlight is just doing something like this. So the limit from that, I think, is it's about 10 to the, what is it? Now I'm forgetting a little bit. I think it's about 10 to the -7 or -8 of solar mass. Okay, the limit. So that's sort of if dark matter particle is bigger, heavier than that, then there may be, maybe ruled out by the microlensing searches already. So
how could we even tell that from a black hole?
Dark matter can be black hole. There's no problem. Okay, well, I mean, let's not get into that discussion. Okay, there's a set of candidates called primordial black holes. So you actually can actually be dark matter. Well, I think you will have a lecture just on dark matter models in the next week. So, yeah. So the solar mass is 10 to the 57 GeV. Okay. So dark matter is 10 to the I don't know. Let's just 10 to the 51 or 50 GeV. Okay, that's allowed. Okay. So what's the lower bound of dark matter mass? Right. So something around that order. Where does it come from? So what do we want dark matter to do? Right. So do we want dark matter to be able to see the structures? Okay. So in order to see the structure, dark matter particle at least has to be smaller than that structure. Okay. So the de Broglie wavelength of a dark matter particle has to fit in like some of the smallest structures we think that's seeded by dark matter. And then you can refine that argument a little bit, and that gave you that number. Okay, basically. Okay, and it's called fuzzy dark matter sometimes. Okay, so it's about 80 order magnitude of dark matter mass. So, and within this whole range of mass, for most of them, we have no hope. Okay, at least based on the current technology, we have no hope to see them. Okay, what we have hope for are a few small windows, very small windows on that spectrum. So just put this into perspective. Okay, so this is dark matter may be very difficult. Okay. So well, I think you know most of the windows. So the window we are going to focus on obviously is called the WIMPs. Okay, so the fact that and the other window is there's another window called axion. Okay, there's some light scalar particle, then there's some other windows. And these days people are trying to, there's a better categorization. You have very light fermions as well. You can also have very light scalars from. So the allowed mass range for light fermions and light scalars are slightly different, because one of them can form both Einstein condensate. The other one, you can only form. There's a Fermi exclusion. Anyway, we are going to focus on WIMPs. Okay, that's the only thing that we have any hope for doing it at the colliders. So WIMPs is this kind of very interesting benchmark. So it basically is the statement that the dark matter. So WIMPs can have many somewhat similar, but actually in detail different definitions. But broadly speaking, it's just saying that there's this particle that couples to standard model with a coupling strength that's not very different from the couplings we have seen in the standard model, and its mass is not too different from the massive particles we have seen in the standard model, and these seems to be reasonable assumptions. Okay, so and you assume that they are in thermal equilibrium in the early universe. No, since they are coupled with standard model, that seems to be a good assumption too, as long as we reheat up to above their mass. And now from that, you already, I think you probably see. I'm sure you have seen that calculation. You roughly get the right radical abundance. Okay, so. And that's why everybody was sort of this is actually it's not just a random benchmark, but it's actually a fairly interesting benchmark. Okay. So dark matter at the colliders. So when I was a student, so we think that I guess we are more ambitious back then. So. The generation of our advisors are more. My advisors are more ambitious than we are, and you always wanted to solve everything all in one thing. So dark matter is usually part of some big, very comprehensive model. Okay, and that model solves everything, and they also have dark matter. Okay, so that is it can be SUSY, it can be some extra dimensional model with some symmetry and so on. Okay, but it's just typically, for example, in SUSY, what do you do? What you see in dark matter is that maybe you can, I don't know, you produce gluinos and they decay, and this may still decay. I don't know. They may give you a W and so on. But this is the dark matter at the end of a long decay chain. Okay, so there's some decay chain and so on. So this is the signal. Okay, so the rate is decent because you produce color particle to begin with, and the signal is good because you have multiple things in the event. You have lots of things in the event. Okay, so and this is good for compare with standard model, because in standard model literally produce one thing, you it's not so easy to add one thing to it. Okay, but this one it's just once you produce the gluino, you get the rest of them for free. Okay, basically it's just decays. Okay, yeah. So if that's been discovered, so we solve all the problem in one single discovery. This is our solution to hierarchy problem, and then we also have dark matter as a missing energy at the end of the decay chain. Okay, so that I think that is used to be the picture. Let's see, what do I want to do? I mean, it's still possible. We haven't made that discovery yet, but it's still possible. Okay, this is but this type of dark matter collider physics is not different from just typical SUSY phenomenology. Okay. Now, the fact that the picture starts to changing a little bit gradually in the past 2 decades is you know, there are several reasons. Well, first of all, it's just perhaps now people are, you know, you wanted to think what is the most really the signal of dark matter. Okay, what is a sort of model independent signal of dark matter? So you think that because I have because WIMP actually relies on this just, you know, this kind of picture, right? I have to have this reaction for the WIMP to stay in thermal equilibrium in early universe. Now perhaps I can just, you know, perhaps this is the collider, and I'll just produce WIMP like that at the collider. So this seems to be the basic channel if you think about WIMPs. Okay, so. But of course, if you do this, you see nothing. Okay, if you just do this, you don't see anything. So you need to recoil against something. Okay, that something can be a jet, and can be a photon and Z and W and Higgs or whatever. You know, this is called the mono X. Okay, mono X search. Okay, so there is a mono jet, mono whatever search, and this seems, you know, it is true that this is somewhat a more model independent channel if you just wanted to say I wanted to look for dark matter. Okay. Let's see what I want to say. Well, we'll talk more about this this soon. And it seems to be, you know, pretty generic, even for SUSY. Okay, even for SUSY, if you just take the dark matter part of it, and it will actually give you this as well. Okay, so, and this is the standard search channel for dark matter at the colliders. Okay. One more comment I wanted to make is that even if you see this, okay, let's say we made a discovery, okay, with the monojet plus missing energy, and in this channel, you actually don't really know this is dark matter. Okay, you only know that the lifetime of this guy is longer than 10 meters. That's the only thing you know. Okay, which is much shorter than the lifetime of universe. And yeah, so it's even if you discover this can only be one hint that we might have discovered dark matter. To actually, you know, confirm that this has something to do with dark matter, you need a lot of other things. Okay, you need to start to make models. You wanted to make a measurement of these couplings. You wanted to, you know, maybe see them in direct detection experiment. You wanted to calculate their relic abundance and so on. So you wanted to do a lot of things. You wanted to predict their contribution to cosmic ray detections and so on. Okay, so I think both of them you will have lectures to cover the other experiments later. So okay. Right. Now let's see. But so the first set of study to actually try to do this is to use the so-called effective operator approach. Okay, so in the sense that you just write operators on this. Okay, you just write a bunch of operators. You say, okay, so maybe I have a QQ bar. I'm just making it up. Okay, just let me have an operator like this. Okay, so you can. And you can put any, you know, Dirac structure in it, you know, as allowed and so on. Okay, you can write this a bunch of operators. Okay, you just say my interaction between dark matter and the standard model is parameterized by this. Okay, now, then you can just do, you know, just use this and calculate the model jet rate. Okay, just okay. Some of the motivation of this is that, of course, this is very simple. This is very simple, and you can also connect between different experiments very easily with this operator. Okay, because you can imagine time goes this way. It's a dark matter scattering on some standard model particle. This is a direct detection. Okay, and if going that way, it's indirect detection, and going this way is a collider. You can connect all of them in principle. Yeah, in particular, you can connect them with a direct detection experiment. So let's say this is some direct detection experiment. Xenon, for example. Okay, so and the limit of direct detection. So this is a limit on some nuclear cross section, dark matter nucleon cross section, and this is dark matter mass. It's always presented in a figure like this, and the limit always goes like this. Okay. So let's see, where is my? Let's understand this a little bit better. Okay, so the reason there's some feature here, right? So the reason that it gets much weaker, it's because the dark matter momentum. This is the dark matter momentum when it's coming in. Okay, when it's coming in, hit the nucleus, and this v is 10 to the minus 3, about 10 to the minus 3. That's the variable velocity of dark matter in the galactic halo. And sorry, I should say that it's the bottom here is about 100 GeV, and it really craps out around 10 GeV. Okay. But when dark matter is 10 GeV, it just roughly speaking, it just hit a nucleus and bounce back. Okay, the nucleus is much heavier. Xenon nucleus is much heavier than this, so it just so the momentum exchange is basically just times 2. Okay, that's the momentum exchange, and the recoil energy. So the nuclear recoil energy is just a delta P square over 2 times m of the nucleus. Okay, that's the amount of energy, the recoil energy, and so you see that when the mass becomes very small, the recoil energy becomes very small. Okay, so all direct detection experiment has some kind of a threshold. Okay, so this is basically the threshold that you start losing sensitivity. Okay, so this curve actually is very steep. If you look at it, it's basically you are getting very close to the threshold, and you shouldn't really believe the behavior here too much. That is, but other than the generic fact that it's losing its sensitivity. And here, on this side, it's actually different. On this side, it's just my dark matter is very heavy. Okay, my dark matter is very heavy. So it's basically the nucleus coming in and the bounce back. Okay, so the momentum exchange does not depend on the dark matter mass. Okay, it's just the nuclear. It's just the nuclear mass. So here the delta P is twice of the nuclear mass times V. Okay, in the dark matter rest frame. Okay, and the momentum exchange does not depend on dark matter mass. But why am I losing sensitivity? Because my detection rate is proportional to the local density of dark matter. Okay, and the local density goes like 1 over m. Local number density of dark matter. Okay, so this is basically just 1 over m. Okay, so anyway, it always looks like this. Okay, yeah, I'm not sure whether you will have a lecture, talk about this in more detail. So let me not go into too much Yeah. So, but the basic feature is that you're losing sensitivity here. Okay, for light dark matter. And on the other hand, for colliders, for this kind of experiment, for this kind of process, it actually doesn't matter how well when this is light, your limit is independent of the dark matter mass. Okay, so usually you have to put some cut on this object to be able to trigger on it. Okay, then once you put that cut, usually this is hundreds of GeV on this object, and this at this kind of mass, you should just think about dark matter is massless. It doesn't matter whether it has mass or not. Okay, so therefore for colliders, the limit for the collider limit here it's usually flat. Okay, so this is the collider limit. It's flat. Okay, but of course at some point this mass becomes important. Okay, you wanted to, it starts to cost you extra energy to produce heavy particles. Okay, so at some point your production rate start to die. So so this is usually the mono X limit. Okay, if you can put them on the same figure. Okay, so this connection again, as I said, this connection is the easiest without additional assumption. If you just write like some effective operator, I don't know. Okay, so let's say a dimension 6. Okay, let me just say, it's fermion dark matter. I write dimension 6 operators. Okay, so yeah, so you can just do this because from this operator you can calculate both the nucleon cross section and the collider cross section. Okay. On the other hand, there is a bit of a problem with this. Okay, it's not a you have to be really careful that if you wanted to use this. Okay, because because this is a non-renormalizable operator. Okay, its effect is more important. The effect of non-renormalizable operator, the effect is more important at the higher energies. Okay, at some energy, this operator shouldn't work anymore. Okay, this operator becomes strongly coupled. That's the energy where you shouldn't trust your theory anymore. Okay. So in other words, this operator, the amplitude you get from this operator should go like something like a e square over lambda square. Okay, so if this is something like a 4 pi and this is too big. Okay, so you shouldn't trust this operator anymore, and you should actually talk about the UV completion of this operator. Okay, so what have you integrated out? Okay. Now then you really need to be careful in order to use this. Okay, there is a self-consistency check. At least you do this, and you set a limit, and you see what the lambda limit you get. Okay, you wanted to look at that. So typically lambda is hundreds of GeV. Let's say. Okay, if you wanted to use this kind of this kind of approach, and this is suspicious. Okay, whether this would work or not. Okay, because typically the energy scale that I used involved in this collision is also hundreds of GeV. Okay, so this is a typical limit. So I'm glossing over a lot of details, but this is typical energy. Okay, and they are on the same order, so it's not clear that whether this operator works or not. Right? And if it doesn't work, then you have to now we get into the game of what the the experimentalist play. Okay, so you have to decide what do you do. Okay, one way is to throw away those events at higher energies. Okay, throw away any event at higher energies that will invalidate this limit. So you have to do this iteratively. Okay, you throw away some event, and then you check the limit on lambda again, see whether the energy is again check whether effective field theory works or not, and if not, you do it again. You have to do this iteratively. Okay. And by the way, so these operators at direct detection, that these are perfectly reasonable things to do. Okay, because again, the momentum exchange involved in the direct detection is this. Okay, usually it's hundreds of MeV. Okay, so it's that is very, very low energy, completely valid. It's just when you do the crossing to this channel, and usually it's not. Well, okay. There are other reasons why I think this approach is not actually very useful. There are still. I'm not saying this is completely invalid. Okay, so, but there is there are corners of parameter space where you can see the limit can actually be approximately by using this operator. But in general, I think this is not very useful. Okay, and so, but let's go on. Okay. We'll come back to that thing. Okay.
Why was the dark matter written as a spin 1/2 field?
It doesn't matter. It doesn't have to. I can write a scalar field too. Then it's just a different operator. I think q bar q chi. Let's say this is a scalar. Then this is a dimension 5 operator. Right. So you can write a Higgs. Now you want to do our Higgs model. Now this is a renormalizable operator. Okay, that's an exception to the other ones. Okay, so but let's think about going. I think the logical next step is to really think about what do we really expect? What are the things that the dark matter will have? What is the one step beyond this very simple approach? Means that I just talk about the standard model particle and the dark matter particle, nothing else. Okay, it seems to be at least at the collider studies that approach is not terribly useful. So the step going beyond. So in these days, usually it's called simplified models. Okay, so it's basically by taking the minimum ingredient beyond that approach, and yet you're talking about a really much more healthy theory at least at the collider energy scales. Okay, so simplified models. Okay, so there are two classes of simplified models. One of them is, I think, it's maybe slightly better appreciated than the others. Okay, the first one is dark matter is part of a electroweak multiplet. Okay, because it's part of an electroweak multiplet, we can just write their interactions with the standard model gauge bosons. Okay, and through that it couples to standard model. Okay, so that is once I say that single word. Once I tell you what the multiplet it is, and you can write all its interactions. Right. The second one is that I'm still talking about just dark matter as a singlet. Okay, just on the other hand, in this case, I need to tell you that what is the sort of the mediator between I need to add a mediator as well. In general. Okay. Well, I guess you can decide which one is the simpler simplified model. Okay. It seems to me the first one is the simplest because I roughly speaking, I made a choice. I make a discrete choice. I fixed everything. The second one is still I need to add 2 particles and with some free parameters to it. Okay. Okay. Now, let's talk about this first. Okay. So the first case. So perhaps we can, just have some examples. Okay. So we can have a doublet, maybe, or triplet. And but you can have other things too. Okay, so you can have other more higher representations as well. And these guys all have names. Okay, these guys all have names other than doublet. Okay, this is also known as a hexeno, and this is also known as a weno. Okay. But you don't have to think about they are part of supersymmetry. Okay, they are just if you forget about the SUSY relations, they are just that. Okay. And yes, you can do mono X search for these guys. And yeah, so for example, you can do you can do this kind of production. Let's say for any of these. So typically a larger cross section is it goes through a Z. It goes through a W. For example, you can produce a chargino and a neutralino. Okay, and then it decays to chi0. Okay. But if I just talk about a almost pure hexeno, or if you worked a little bit with SUSY, you have experienced that the splitting of these two are very small. Okay, so this is some soft stuff. Okay, for the moment, let's pretend that we don't see those things. Okay, so that's I'll come back to this point later. But then the only thing you see is jet or something else. Okay, so this is roughly speaking a mono X. It's still a mono X thing, and with some soft stuff. But soft stuff is in many cases hard to see. Okay. The limit of LGC that can set. So first of all, the only free parameter here is the mass. Okay, so there's only one free parameter here. It's the mass of the LSP. Yeah.
Although it's soft, you see it because it's charged.
Huh? Yeah, but there are many charged particles. If you just have, I give you 100 MeV pion, it probably won't be able to see it.
Okay.
Yeah. So, well, I'll come back to this exact point later. Okay. So, but let's for the moment let's think about it as not observable. So there's only one free parameter, which is this. Okay. There's no mediator and so on. The mediator, we know what the mediator does. Okay. Mediator is just our standard model gauge bosons, and the limit is terrible. Okay. The limit is I think at the LHC 8. Okay. LHC 8 TeV. And for this. The limit is 0 GeV. There's no limit, no sensitivity to this. Okay, because it's we'll talk about why is that the case. Okay, immediately. So, but and the LHC at the LGC 14 and a 3 inverse autobahn. Okay, ultimate reach. Okay, on this channel. I don't know. Let's call it 200 GeV. Okay, it's actually depends. Okay, so let's try to talk about this a little bit more. Okay, so so what are the background? What are the backgrounds of this? Okay, let's think about monojet. Okay, so typically monojet give you the best limit. Okay, so let's think about the monojet. So the background is jet plus z when z goes to neutrino. Okay, and this is about this is a suppose you have to put a cut on the jet. Okay, so typical PT cut is greater than 250. Okay, GeV, and well, typically you also require missing energy to be bigger than 250. Okay, so these two are not very different, by the way. Okay, they are certainly correlated, because if you don't have anything else, okay, the PT of this jet is exactly the same as the missing energy. Okay, you don't have anything else observable. Okay, the missing energy actually is independent of the mass of these guys. Okay, the missing energy is just the momentum of this guy. Okay. Now, in this case, so this is about a picobar. Okay. Just you can look it up, or you can do an exercise. Try to just scaling from PDFs as we did in our earlier lecture. Yeah. Where, well, there are also like a jet plus W and so on. These are all at around the same level. Okay, jet plus W with L nu, but you're missing the lepton. Okay, this is actually the similar level. Okay. On the other hand, the production of this guy, of this, okay, the production of this. So a jet plus chi, okay. You already just from this very simple-minded argument, you already see this should be much smaller than that. Okay, I have 3 things here. Okay. I only have 2 things here. Okay, the decay is 20% branching ratio. That's not a suppression, right? But I have to do 3 things here. Okay, so this is usually less than, well, it's usually a few percent of the jet plus Z. Okay, so the cross section is very small. Compare with your background. Okay. Now this is not necessarily a big problem. As we said, there's another way of discovering new physics is to have some shape. Okay. Even when you have shape, even if it's rated small, it's not a big problem. But on the other hand, there's really no feature here. Just think about this process. There's no feature. You only have a jet. Okay. Or maybe 2 jets, but it doesn't matter. So there's not a characteristic scale. There's not a something you can say, I can form some kinematical variable for this that has an obvious scale. Okay. In fact, the way you add a jet on top of this is very similar to you add a jet on top of a z. Okay. It's not coming from some decay and so on. There's no characteristic mass scale here. Okay, so the distribution of these jets is just as smooth as a standard model. Okay, so so you can look at the figure. So basically, basically, if you want to plot a matter distribution, this is like a z. Okay, this is jet plus z, and this is dark matter. Okay, and it's just a few percent difference. Okay, so it's actually very difficult to do this. Okay, but so remember, in order to do this, this means that you need to know the error on this guy to a few percent. Okay, and I would see at this moment, I think forget about it. I think if everything with the same shape, they will say it's not, because it's very hard to trust your Monte Carlo generation simulation for this, and to actually can reproduce the actual experimental result. So that's why this is I just want to say this is a very difficult channel. Okay, even if so in the future, I think they will do better. They will start put limit on these things. Okay, I haven't looked up yet. They may already have some limit on this, maybe 100 GeV or something. On the other hand, you should always be suspicious of this limit. Okay, because this is assuming that. Okay, I'm sure they know what they're doing, but it's still a little bit suspicious because they're assuming you're assuming that the background, the shape perfectly well. Okay, because any attempt to fit that background will just get rid of. Yeah. Okay.
Sorry, maybe this is already implied by something on the board, but why couldn't you see some sort of resonance near twice the dark matter mass?
Okay, so how do you see that resonance?
Why wouldn't you see any feature there?
Oh. Why should you? I don't know. It's just I'm
threshold production.
Well, this too wants to produce at the threshold,
Yeah.
but the energy of this jet is the only thing you see. Okay, it doesn't know that yes, it does want to go to zero, but that's the part of the diagram you cannot look at. Okay, another way of saying is that this jet, the kinematics of these two jets are not too different. Other than that, other than the fact that this happens at a slightly higher scale than this. Okay, there is a bit of a difference, but that difference is logarithmic, typically. It's some log of energy scale. That's the difference between these two. So that's a very mild difference. Yeah. Okay. Now, maybe this is a point to sing some praise for linear collider. Okay, because at the linear collider this is possible. At the lepton colliders, this is suddenly becomes possible. Okay, so lepton collider, basically you do a very similar thing. Okay, at the lepton collider, you do E plus E minus, gamma Z, gamma star Z star. You do the charge production, okay, or neutral production. I don't know, because neutral sometimes couples to Z as well, and you do decay. Okay, but let's even assume you still don't see these guys at the lepton colliders. First of all, it's much easier at the lepton collider to see these soft things. But for the moment, we can even assume you still don't see it. Okay, let's say you don't see it. Okay, then I do need to do something else too. Okay, let's say I radiate a photon. Okay, but the only requirement becomes that I need to see this photon. And this photon needs to be more energetic than my photon threshold at the lepton collider. Okay, at the lap this is about 10 GeV. Okay, so the limit at the lepton collider, for lepton collider, the limit on the dark matter mass is roughly speaking the center of mass energy of the lepton collider divided by 2. Okay, well, minus this photon threshold, but that's usually a small number. Okay, so if you look it up, lap searched for this. Okay, the lap limit on this guy, I think it's about 95 or something. Okay, so roughly speaking, lap energy minus their photon threshold divided by 2. Okay, so means that this is again, as long as you can see them at the lepton collider, you discover them. There's no you don't worry. Well, there's still background to worry about and so on, but just that's that. Okay, but on the other hand, it is constrained by this, by the center of mass energy. Okay, suppose I have a TeV ILC, which is perhaps very futuristic, and the limit you can set is roughly about 500 GeV. Okay, 3 TeV click, I can set a limit on 1.5 TeV. Okay. Yeah, lepton collider physics can be taught in 1 minute. That's why we need the lepton colliders. Okay. Anyway, okay. So of course you can go up in energy. You wanted to go up in energy. So if I have 100 TeV PP collider, okay. So the limit on doublet is about you can actually go up to 1 point something TeV, go up to 1 TeV, okay, and limit on triplet is slightly better than 1 point something TeV, okay, just from monojet, okay. Now again, so you look at these numbers, you say, so what, right? What is the mass we think these things are? Okay, what are the masses? So just to calibrate, is that if you literally want this guy to have the correct relic abundance, literally want that, and for this is 1.2 TeV, for this is 3 TeV. Okay, if you literally want that. Okay. So, of course, there's some model dependence, right? Maybe you have some non-thermal production as well. You maybe you have some late time entropy production, dilute some of them, and so on and so forth. But but roughly speaking, still you wanted to go to TeV to actually test these WIMPs at least. Okay, where LHC is not the right machine to do it. Okay, unfortunately. Okay, if you really literally wanted to go to TeV, LHC will do something, but really this is one of the arguments for high energy proton colliders. Okay. Okay. Now let's come back to the other point that someone already raised. That let's see whether we can do something about the fact that there is still a step of decay here. Okay, let's see whether we can do something about it. Okay. Now, let's see. So first of all, let's ask what's the mass splitting? What is the mass splitting between the charge and the neutral guy? Okay. So let's talk about the doublet just for example. Okay, so let's see. We have a doublet. Okay, it's just like a standard model lepton doublet. Okay, and it's vector like. So this is my mass term. Okay, so this is the universal mass. Okay, and then obviously there will be radiative corrections to it. Okay, so even if this does not directly couple to the Higgs boson, it will still have corrections due to electroweak symmetry breaking. Okay, at the one loop level, okay. You will still feel it. More specifically, I can do this. For example, I can do L plus. This have gamma in the Z diagram. Okay, and also so this is L plus, and this has a Z. L0 also has a Z in it. Right, so this is a. Now you can also have a W diagram. A W if you start with, you can start with L plus or L0 here, and inside it there will be a L0 or L plus. Right. So that will be a W diagram. But W diagram, this one does not generate mass splitting because it couples to charge and the neutral in a universal way. Okay. It does shift renormalize the mass, but it does not generate a splitting. And these two does generate a splitting. And so let me just write the answer. Delta M times a function. Okay. And this R is M over mz. Well, it's some ratio of this, okay? And this function actually goes to 1 as R goes to infinity. Okay. This means that when the mass is heavier than z, and this asymptotes to a value which is 2r from mz. Okay. So you can understand this if you think about it in terms of low energy effective field theory. You will see that the photon diagram of this is actually linearly divergent, and that linear divergence is cut off by the Z diagram. Okay, that's why it's proportional to this. Right, so I guess it's a good exercise to try it yourself. And this guy goes to a mass splitting of 355 MeV. Okay.
Why shouldn't we be considering a coupling to the photon?
Huh? Photon, you mean?
Yeah, to the photon.
Photon, yeah. This is charged.
Okay. Is it still dark matter?
No, this is the dark matter.
Okay.
Yeah. It's not stable. It's not stable at the charger one is not stable on
Just making sure I'm not
yeah.
crazy here.
Right. So yes, if you somehow you can reverse the order of these, the mass order of these two, then we'll be in trouble. Okay. then this is not dark matter. We need to find a way to make it decay. Maybe by mixing it, we'll mix it with some standard model lepton or something. So, okay. But for triplet, there's a similar calculation, but it just give you a different answer. I don't remember the exact number, but it's something around this. Okay. Also in the limit when the triplet mass gets heavier. Okay. But remember, I just erased it. The interesting scenario for the mass is around the TeV. Okay, so this is actually the interesting scenario because it is always quite a bit heavier than Z. Okay, so these are the canonical numbers. Now let's consider this guy decay. Okay, now let's consider this guy decay. How does this decay? What does this go to? Well, you will say this is couples to W plus minus, very off shell. Okay, very off shell. Let me put 2 stars here, and there are these two quarks. Okay, 2 quarks, and but they are very close by because they are confined. They are very the phase space here is very small, so they really just bind into a hadron. Okay, the hadron falls into this mass range is pi plus minus typically. Okay, so a slightly better way to think about this is to do this, and you say I'm coupling to the goldstone. Okay, the goldstone of W longitudinal, and but the longitudinal W mixed with pion. Okay. I don't know whether you have thought about this way or not. The goldstone couples like a derivative over V. That's the coupling. And then this mixing goes like a F pi over V. Okay, F pi is the pion decay constant. So, yeah, so from that one, it's easier to justify what I'm about to write down. Okay, so now, and so that one is so the width is 4 times d square minus 1, and the gf square over 4 pi. And Christoph already tell you what the gf is. It's basically 1 over v square. I forgot where the square root of 2 goes, but you know it's 1 over v squared. Let's just say. And this is some Cabibbo angle, but this is about 1. Okay, it's not the f pi square. Yeah, so basically I have f pi over v square. It's coming from this mixing. And now let's think about the dimensions. So this is 1 over v to the 4th. This is f pi square. So I want to get the width, right? So width has a dimension of mass. So the only other dimension for quantity here is the delta m cube. Okay, and if you do it carefully, there is a phase space factor. Okay. Okay, turns out to be this. Okay. This is just saying that if the mass gap is getting too close to the pion, you get a suppression here too. Okay, and the suppression goes like the square root. Okay, so okay, and the d is the dimension of the representation. Okay, so 2 for doublet, 3 for triplet. Okay, but the determining factor here is really this guy. Really what the mass gap is. Okay, that's the determining factor. And okay, so let's look at the lifetime. So lifetime for doublet is about a centimeter. Okay, for triplet is about 10 centimeter. Okay, so that's the okay. All right. Now we'll see these two numbers are actually very different. Okay, well, one is different from 10, but you know it's actually very different in the following sense. Okay, so you can see that this is certainly a displaced vertex. Okay, if you know what I mean. So it's very displaced decay. Okay, but let's think about what does it do? Okay, so it's some chi plus. Okay, and go fly for. Well, there's typically a little bit of boost, but let's say it's a few. Gamma is a couple. Okay, so the boost factor is a couple. So it's still a few centimeters. So you fly for a few centimeters, and decay to a pion. By the way, before I go there, you may want to ask, why can this go to a lepton and a neutrino? Okay, the answer is yes, but the branching ratio is much smaller because that is actually authentic 3-body decay. Okay, and this one is actually a 2-body decay. So the 2-body usually completely dominates, if it's allowed. Okay. So let's see this, okay, and then you decay to the. You don't see this, you don't see that, and you see a pion. So what you see is in a detector suddenly a few centimeters away from the interaction vertex there's a pion. Okay. So that may be an interesting an interesting signal. Okay, and so first of all, so this pion still tends to be quite soft. Okay, because from phase space it only get on the order of a couple hundred MeV, MeV of energy. and then there's a bit of a boost. So it still wouldn't be, so you have a less than GeV pion, okay, in the detector. So it does a bit of something like this. So it's still pretty hard to see. First of all, you can definitely not trigger on this, okay, and usually you need to still have a very hard jet. So you still do mono jet, but the idea is maybe you come back and look for a highly displaced pion, okay. That has been talked about as a potential signature for this, but so far we haven't been able to do that yet at LHC. Okay, apparently this one still has a lot of background. Okay, just the highly displaced vertex. So hopefully, my hope is they may be able to do something about this later. Okay, but now you see that the difference, there are a little bit of a difference between these two. Okay, the difference is that my layers of detectors are actually, roughly speaking, 10 centimeter away. Okay, I don't remember the actual numbers. Okay, so but it's roughly speaking, it's 10 centimeter away, the inner trackers. Okay, so if I do live around the 10 centimeters with a little bit of boost, this is what I will do, right? So I will fly to here. My chi plus can fly here and then decay. Okay. Okay. I may still not see the pion, but I do see a charge track. Okay, stop in the middle of my detector. Okay, so that turns out to be a very distinct signal. Okay, so even okay, I don't think they can trigger on this yet. You still wanted to radiate the jet, but they may be able to trigger on this later. But the name of this is called the disappearing track. Okay, so that is very useful. Okay. So it's very strong. Okay, so at LHC, using this disappearing track, I can already set a limit in the Wino case. In the triplet case, the limit is I don't remember the name. Let's call it 300 GeV. Okay. Maybe 250, but remember this is comparing with this is still not quite where we want it to be, but this is much better than in the monojet case. So we have 0, right? This is at least a solid limit. Unfortunately for Higgsino, for doublet, it's more difficult. Okay, you can still try to maybe I can pay to on the tail. Pay some additional price to live on the tail and because the lifetime is 1 centimeter doesn't actually means that every one of them decay at 1 centimeter, right? So it's some exponential tail I can try to live on and so on. Then we can try to do something. But at LHC, I think the limit is still pretty weak, just based on from that. And at 100 TeV collider, you can actually try to do that. Okay, so because the rate is high. At 100 TeV collider, if you apply this to triplet, this actually starts to go to 3 TeV. Okay, the 3 TeV is where remember where we want it to be. Okay. Okay.
You mean the 100 TeV detector with the exact same configuration?
Not exactly. This is a very rough extrapolation. So okay, so I think this is just based on rate, just based on some rate, and yeah. So presumably 100 TeV can be much better than RHC. So maybe I'm optimistic that it will probably cover the doublet case very well as well. Okay, at 100 TeV. What else I wanted to say? Okay, yeah.
Would help somehow to get a bigger mass difference between the L plus and the
Yeah, okay, let's come to that. Okay, let's come to that. So at this level, that's it. Okay, at this level, that's it. Now you can say, oh, maybe this mixes with something and so on, right? This can mix with some things. For example, in SUSY it can mix with Bino, right? At the the Hexeno can mix with Bino, and the Wino can also mix with Hexeno, and so on. So it's supposed to have some mixing. Oh, so first of all, if I have multiple of them around, okay, then my life becomes easier. Okay, if I have both of them are light, okay, then I can produce them. This guy decays to that guy, give me some leptons and so on. That's much easier to search in that way. Okay, but if even if I just play with the mixing, I can change the mass gap. Okay, it's much easier to change the mass gap for doublet than the triplet. Turns out. Okay, so it's just easier for. But slightly easier. I shouldn't say much easier. Just slightly easier to change the mass gap. But I think a more promising direction to change the mass gap is to make it smaller. Make it smaller, then it's actually much easier to see because the lifetime is longer. The charge guy has a much longer lifetime, so you have a longer track to look for. But it's a little bit fine-tuned. I think the best, the simplest case are still just the ones that I talked about. Okay, now let's come to the second kind of simplified model. Okay, just I add one more particle, add some mediator, and I add a singlet. Okay. So what I can do is, for example, perhaps I will start to have this kind of cup. Well, okay. So I'm going to add a particle here. Okay. Yeah. I don't know. Perhaps I can just call it a Z prime. Okay. Just I'm not even implying that it has to be spin 1, but it's just some S channel propagator. Or I can do something like perhaps like this. Oh, which way I draw this diagram? Q chi. I can do something like this. Okay. So I can add something here, and so this, drawing this way, it's obvious that why this is called the S channel diagram, S channel models. So this is called the T channel models. Okay, and this guy obviously has to be colored. Okay, so I don't know. Let's just call it a Q. Right. So, well, let's just talk about this in a little bit of detail, okay? So, let's see. So obviously now I have all these free parameters, GQ and the GX, okay? Okay, and I should also there are free parameters also the mass of this guy and this guy. Okay, yeah, perhaps I can just draw the picture that you can take a look. Okay. Okay. So. So this is mx, this is m c prime, okay, and this this is the line of 2mx equals mz prime. Okay, so let's see the monojet. This is the monojet limit. And the monojet. Let me erase this. So for monojet, what you do is you just produce the z prime, and then you radiate a jet. Okay, that's your beginning process, and this is and then this decay to dark matter. Okay, so this is your monojet, and so there are a few things. First of all, it's pretty obvious that why you don't have much of a limit when the dark matter mass is bigger than half of the z prime mass, because in that case this is off shell. Okay, so you're actually doing a 2-to-3 production if this is off shell. So the rate is much smaller. The signal rate is smaller, so you don't have much of a limit above that line. And this line stops at about 1.5 TeV. Okay, so this is basically the line that this is basically the where you stop being able to produce this this z prime. Oh, by the way, this figure has a choice. Okay, so this is the Atlas result if you want to look it up. The Atlas, the most updated Atlas result, 13 TeV, 36 inverse femtobarn. Okay, and so we'll come back to why, what happened if I make a different choice. Okay, and this is monojet. Okay, so let's just try to do some sanity checks of that result. Okay, so the signal rate, signal of producing a z prime. Okay, producing a z prime of 1.5 TeV with that coupling. With that coupling is about the picobar. Okay, with this coupling, this QQ bar, you can scale that from for example Z production. Okay, and it's just the coupling is smaller than Z. Okay. So signal is about 1 picobar, and the background. Sorry, it's about it's less than that. Yeah. Sorry, I shouldn't say this. Okay, it's a picobar, but then I have to add a jet. Okay, add a 250 GeV jet. Okay, so at least I will pay some factor. Okay, let's say now let me even be generous. I'll say this is a few times 0.01 picobar. Okay, it's roughly around this order. Okay, the signal is around this order. Okay, and the background is a Z plus jet. Okay, and this jet. By the way, this jet is 250 GeV again. Okay, background is Z plus jet. Again, you can do some scaling with the PDF and so on. So just again start from Z production. So start from a Z production. And you want to add a jet, and you want to remember that the S hat is about 500 GeV. Okay, just because you add a 250 GeV jet, you recoil against the Z, and the system, the total energy of the system is about 500. Okay, so you wanted to do that, and this give you this background is on the order of picobar. Okay. Yeah, so this looks pretty difficult. Okay. It looks pretty impressive that they can actually set a limit around here. Okay. So maybe they can, but I'm a little bit suspicious. Okay, so but maybe they can. Okay, that's monojet. On the other hand, you already see that in this case, dark matter is not the only new physics particle. Okay, I have another new physics particle to look for. Okay, I can look for that mediator. In particular, I already assumed that there is a QQ bar Z prime coupling. Okay, I should be able to just do this. Okay, I just do a dijet search. Okay, dijet resonance. This is a dijet resonance. Okay. So again, let's do an estimate of of the reach of this guy. Okay. Again, I'm going to take these benchmark values. Okay. Just do it. So yeah. So first of all, you see that the cross section of this guy is proportional to GQ square, then the branching ratio of this guy going back to QQ bar. Okay, so GQ square to GX square plus GQ square. Okay, but this is about a GQ to the fourth GX square. Okay, taking the value that we do we over there. So GX is much bigger than GQ. So I just ignore the second term on the denominator. Okay, so but let's take that, and you can either calculate the rate, or again you can scale from the z and so on. So sigma z prime times branching ratio. Okay. And remember we say that this is a picobar. Production of sigma z prime is a picobar, but there's a bit of branching ratio here. Okay. Well, at least there's a okay. So let's what's the number I should say? Yeah. Let's say it's well. Let's say it's 0.0 picobar, 0.01 picobar. Okay, let's just say that. Okay. Now, dijet. The background is obviously QCD dijet. Okay. We have said that at the first class is QCD dijet with 250 GeV. PT is 100 nanobar. Okay, then we can scale that cross section, literally based on PDF. Okay, so it turns out. So it turns out that the dijet at 1.5 TeV is about 100 picobar. Okay, at that point. Okay. Oh, you say this is even worse, right? Than the other one. Okay, but it's different. Remember, this is a bump. This is a resonance. Okay, there has a distinct shape. Okay, I'm going to rely on that shape. Okay, but once I rely on that shape, I'm really not talking about the S over B. Okay, I'm really talking about S over square root of B. Okay, square root of B is basically a statistical fluctuation. Well, there's still some systematics, but roughly speaking, I'm comparing S over root B. Okay, so let's calculate S over root B. Okay, so for let's say for 10 inverse femtobar. Okay, just to have easy numbers to carry. Okay, so there's always order 1 numbers here. So 10 inverse femtobar. Okay, what is it? This is 10 to the 3 events. Okay. I mean, in reality, we have 3 times 10 to the 3 events, and so on. Okay. And in reality, this is actually a little bit smaller than this. Okay, it's not 100 picobar yet. Okay, so but let's in this case, I have a for 10 inverse picobar. Actually, here I have about 10 to the 6 events. Okay. So signal is, at least even with this little bit of a conservative estimate, because this rate I think overestimate a little bit. I underestimate this a little bit, and then right now we have 30 inverse femto bar rather than 10. Okay. But even here you see it's within striking distance, right? S is the same order as the root B. Okay. So it turns out that dijet search completely rule this out already. Okay, it's completely ruling this out. Dijet is something. It's out already. Okay. And there's a yeah. It's very, very low. There's a little bit of a gap at a very low mediator mass. Okay, but that's yet another story. So, but okay. So let me make some comment. Okay. So now what is the signal rate? Let's think a little bit further about what the signal rate is. Signal rate goes by GQ square, GX square plus GQ square. Okay. So signal monojet. So this is monojet. Okay, this is monojet rate. The dijet rate goes by this. Dijet resonance rate. Okay, so you see that that's why they so there's lots of discussion what is the benchmark number to choose. Okay, and I don't know how many hours we spend on this with the experimentalist, but this is the number. Okay, this is already strategically chosen, so the monojet at least is enhanced relative to that. Okay, so monojet certainly is enhanced by GX square. Okay, the relative strength. Okay, therefore you can still draw an interesting curve here. Okay, but still, even in this case, I think dijet is just much stronger. Okay, obviously you can choose GQ equals to 0.001. Then I think the monojet may actually wins, but then the limit, everything the limit is very, very miserable because the production rate also goes down a lot. Yeah.
Are there some constraints on this coupling constants which you can import, or it's just completely random?
Well, the constraint is dijet searches. Otherwise, I don't know. Otherwise, it's some aesthetics, right? So you say, okay, maybe it's not too small. I don't know. Right, so, and it cannot be 4 pi. It cannot be bigger than 4 pi. Okay, so you don't want to make this to be a million or something. This coupling constant, right? That is problematic. Yes, in that case, your monojet completely wins, but it doesn't. Also, it doesn't win that much because it saturates quickly. This branching ratio, it's just branching. This is already almost branching ratio 1 to dark matter. Yeah. Why wouldn't I say? I would, but I think I already tried to tell you what the reason. That I don't know how many hours, how many email exchanges after that this is the this is the I don't know. Let's call it the community consensus. Yeah. So but even this, you see that the once in this kind of model. Once you introduce a new mediator, usually just looking for the mediator is stronger than looking for monojet. Okay, just because because looking for resonance is easier. Just very simple. Yeah, and it's also true. I think the same lesson. So those T-channel models has not been completely implemented by the experimentalists yet. Okay, they are certainly doing it, but I think part of the reason is there's not quite a community consensus yet about what the coupling constant to choose, what the grid to use, but yeah. So those T-channel models. Remember, the coupling is this, right? So I have a new mediator. Okay. but it's just a name. Okay, you recognize that you can call it a squark. Okay, this is a Z prime. This is a squark. Okay, so you can actually produce the Qs because the Q is colored. You can actually produce them, and this will decay to Q over X and the Q and X. This will decay to that. This is a standard squark search. Okay, so I think in general, again, you can find the corners. You can find the bits and pieces and corners that maybe monojet can still be useful, but in general, you just look for the squark. Okay, you just look for the mediator. I mean, this of course doesn't say that we shouldn't do monojet searches. Okay, we should. Okay, certainly we should, and especially for the first kind of simplified models, monojet is roughly speaking only thing you have for a while at least. But on the other hand, for these simplified models, usually this looking for mediator is more sensitive. Unfortunately, for the first kind of models, we don't have mediator to look for. So because we already found all the mediators, so it's just W's and Z's. So we already found them. So I think this is a very, very quick review of what the LHC is doing to look for dark matter. And there are also additional signals. So these are the simple things. There are also, these days, there are lots of effort on going beyond the simple dark matter models. Okay, just so let's say you wanted to, maybe for some reason you want to have dark matter has its own interactions with dark sectors, dark photons, and so on. Okay, and those things I would say usually, first of all, the message is also that for those things, in most cases I would say looking for these new additional things you add to the model is much easier to look for than the dark matter itself. But searching for the dark matter is still going to be very difficult, literally searching for the dark matter, but you may be able to find some of the other things. So, and for those very light dark sector models, the most sensitive probe is usually not the LHC. Okay, so usually, usually they are very light, but they are still okay because they are very weakly coupled to us. Okay, and those model. Those models can still be WIMPs. Okay, so in the sense that it still has a reasonable freeze out. Okay, so you can still do XX. Let's say this is a dark photon. Okay, darker some sector, and this couples to standard model. But this coupling, let's say, only has a very small coupling constant, which we call epsilon. Okay. But this can still be in thermal equilibrium with standard model as long as this phi is in thermal equilibrium with standard model. Okay, and we can do an estimate. So this is the process that keeps the phi in with thermal equilibrium in the standard model. The cross section goes by is about the epsilon to the 4th over m phi square. Okay, it's in thermal equilibrium with standard model means that this times t cube is equal to the Hubble constant. Okay, it's comparable to the Hubble or less than Hubble. That's where, if you plug it in, if I just take some random value, okay, just take this to be GeV, and take the freeze out temperature, for a typical WIMP to be tens of GeV. Epsilon, as long as epsilon is greater than 10 to the minus 5, for example, and this still works. Okay, so this is still a WIMP story with those dark sectors. But if this is 10 to the minus 5, I think at least colliders has no hope. Okay, and I think but because sometimes this is light, you can try to maybe make them in fixed target experiment. Okay, what you gain in fixed target is that you have lots of luminosity, so to say, because you're just dumping things onto a target, and the limit on that is usually 10 to the minus 3 to 10 to the minus 4. So there's still a little bit of a gap to reach there. But so I think you will have a lecture from Brian on dark sector models. So let me just stop there. Okay. All right. Thanks.